let's see what we've got. A water tank has the shape of an inverted cone. The tank is filled with water, which has a density of 62.5 pounds per cubic foot, or 62.4. I've been seeing either number floating around, so use whichever number you're supposed to use if it's water. And it's filled to a depth of 15 feet. How much work is required to pump all the water out a spigot that is 5 feet above the top of the tank? So we definitely want to draw a picture. So I really don't need to draw the whole cone, but I might. What I mean by the whole cone is like, I don't need to draw the 3D shape. You can kind of just draw a triangle, and that might be sufficient. So here's my triangle, and here's the spigot where the water is getting pumped out. And I want to figure out the work being done to pump all the water. And the water, so I should probably start labeling some things. So I'm going to label it the way I like to label it, and then I will also talk about, so this is actually not from one of the worksheets I sent out. I know I said I was going to use the worksheet I sent out. This is from problem solving, problem solving 9, I believe, in the, if you look at, so actually I want to show you something else in Canvas anyway, so let me go ahead and show you for one moment here. I know I can share my screen. Yes, I am capable of sharing my screen. So over here is Canvas. Yeah, that's not, if you go to modules for a second. So up at the top, I posted the two things. I also sent out in the email, and as well as the solutions. So here's the practice exam, and here's an exam from a different teacher. Although this stuff didn't quite get up to the work stuff, so I feel like this exam maybe not so great. I might post another one later. If you scroll down here, you look at problem solving 9. There are also some good work questions there. So problem solving 9, I'm looking at question 5, although I did, sorry, question, not 5. Question 3. I did make one change. I added a 5-foot spigot to the top because I wanted to make it a little more interesting. That's what we're looking at. So if you want to find it there in Canvas, you certainly can. Where are the answer keys to the problem sets? Good question. Do I have them posted? I might not. I know Grant has them posted. So let me just. Grant also has all the same problem sets essentially posted. So if you go to his website also has the solutions to the problem sets. Okay, so we've got this tank, it's cone shaped, and I'm going to set the bottom to be y equal to 0, and the top of the tank to be y equal to 20. So this is going to be y equal to 25, and the top of the water, right, that's going to be at y equals 15. And then again, we're going to look at a slice of water. So here is a slice of water. We really want to figure out how much work does it take to move that slice of water out the top of the spigot. So to figure out how much it weighs, aka it also known as the force, times how far it goes, also known as the distance. So we've done this a few times. So the work is just, the force is just the volume times the density. So this is going to be really the volume of the slice times the density of the slice times the distance it's going to travel. If you set it up this way, you're saying that this is located at a height of y. It's got a thickness of dy, and it's going to travel 25 minus y. So there's one issue. Well, there's not one issue. So here's what we've got so far. Volume we'll come back to. We definitely got the density as 62.5. And the distance it's going to travel is 25 minus y. The volume is the volume of this disk, which is going to be pi times the radius of that disk squared, which we'll figure out in a second, times the thickness of the disk, which is dy. So there's our volume There's our density. There's our distance. So we have to find that radius. And the thing is, the radius is going to be variable. Right? I've got this small triangle, or cone really, but I can really just draw it as a triangle, whose radius I don't know, and whose height is y. And then I've got this larger triangle, or cone, whose radius is 10, and whose height is 20. So it looks like the radius is half the height. So here I can say, oh yeah, the radius in this smaller cone of water is half the height, which is just y. Or you could do a similar triangle sort of thing, right? Say like r is to y as 10 is to 20, and then solve for r. Whenever you've got a cone situation, you're almost always going to have to do this kind of thing. So my radius here is going to be 1/2 y. So then I can write that the volume of this slice is pi times 1/2 y squared dy. The density is 62.5, and the distance is 25 minus y. Okay. The only thing left to do is integrate. So let me ask you guys, what are my limits of integration going to be? The water is as low as 0 and as high as what? Exactly, 15. But it's easy to make the mistake of accidentally integrating. Oh, someone to admit. Sorry, one second. It's easy to make the mistake of integrating from like 0 to 20 because you're like, oh, it's just the whole thing. So be careful. Right? You're only integrating over the part of the tank where you actually have water. So now we're going to write this. I guess I can go to the other side and write this. So we're going to do this integral. So we're doing to find the work for the entire water being pumped out the top of this spigot. It's going to be the integral from 0 to 15 of all that stuff we just had. Pi times 1/2 y squared times dy times 2.5 minus 25 minus 1. Okay. It's a lot of stuff. Pi 1/2 y squared dy times 62.5 times 25 minus y. Any constant multiple can come out in front. So I can bring out the pi. I can bring out the 1/4, right? Because 1/2 is 1/2 is 1/4. And I can bring out the 62.5. Everything else, the y squared, the 25 minus y, and the dy have to stay. And then we can do the, well, we can multiply this out, I guess. So I've got, let's see, 62.5 divided by 4. I don't know, that's something. I might just write this as 62.5 pi divided by 4 and worry about it later. I'm going to integrate from 0 to 15, 25y squared minus y cubed dy. And then we integrate. We get 62.5 pi over 4. Integral of 25y squared is 25y cubed over 3 minus y to the 4th over 4 from 0 to 15. The only nice thing about this problem really is that at least we've got a 0 for our lower limit of integration, so that when we do this, we're going to get 62.5 pi over 4 times 25 times 15 cubed over 3 minus 15 to the 4th over 4. If I was taking a test that had a limited amount of time, I would probably stop there. And then if I had time later, I would go back and actually calculate it. But I think, you've done all the really important work. We can continue. We can see, let's see, so 15 cubed. Yeah. So yeah, fun time. I don't want to calculate. Yeah, I don't want to calculate this. It's terrible. But we could calculate it. So 15 cubed, I can write this as 62.5 pi over 4 one of the 15s has a factor of 3, so I can actually think of this as 25 times 15 squared times 15. And 15 over 3 is 5. So I can think of this as 25 times 15 squared times 5. And 25 times 15 squared times 5 is 28,125 minus 15 to the 4th over 4 is 50,625 over 4. And then you can finish that on your own, I think. Again, I will say most of the point of these problems isn't so much the getting your final numerical answer as it's setting it up correctly and making sure you're able to integrate it. Yes, it is also important to be able to do this, but at this point it's multiplying this by 4 over 4, subtracting these together, and then multiplying it by that. Yeah. I will point out that this problem specifically, this cone problem, does not lend itself as well to doing the to switching the orientation and saying like up here is y equals 0 and down here is y equals 25. It'll still work fine, but then you have to kind of, the way the radius here works is a little bit different, and so it's going to be a little bit more challenging to do it that way. Okay, I have to erase this one. Let's do a force problem. I definitely have one. I think I have one on this practice test that I actually thought was good. Where'd you go? Sorry, it's impossible to keep track of everything, which I'm sure you guys have noticed. Let's see, where'd you go? Okay, so this is problem 4 from the practice exam 2A. The ends of a water tank are isosceles triangles with legs of 5 feet. The top of the trapezoid is 8 feet and the bottom is 2 feet. The tank is 10 feet long. I can do a spring problem, sure, but let's do this force problem first. So I feel like this is written in a way that the person writing it thought it was really easy to understand, but it's not. So the ends of a water tank are isosceles trapezoids. So isosceles trapezoid means something that looks like this, right? It's kind of your classic trapezoid shape, where where'd you go? Sorry. With legs of 5 feet. And what else have we got here? The top is 8 feet. Bottom is 2 feet. It's not drawn to scale, in case you hadn't recognized that. So we want to find the work to pump the water. Oh yeah, we'll do both parts, sure. Let's find the work. Oh, and sorry, and the tank is 10 feet long. So all right, so there's our tank, kind of like a trough. So there's our tank, drawn really excellently well. And it's full of water. Right, let me see. Sorry, I keep losing where I'm at here because I'm trying to see everything. Sorry, okay. So, yes, how much work is it going to take to pump all of, so where this tank is full of water, how much work to get all of the water out of the tank? So work to pump all water out. So this fact that the fact that this part here is 10 feet long is important, but it's not super vital. So I'm going to kind of redraw this, where I'm just kind of drawing the part that's important, which is really just the trapezoid face. This is 2, this is 8, these are each 5. And I want to figure out how much work it is to pump all the water out. So I'm going to look at a slice of water, which would really be, I'm looking at a slice, it's really this kind of slice here. Whoops, except not stupid looking. Sorry. So it's a slice like that, kind of like a big old like sheet of maybe like like cookies, like not like maybe like make those cookie cake things. It's like a big old sheet pan, like it's just a big old slice of cookie, kind of like that. It's a big old sheet of cookie, one giant rectangular cookie. All right, so we want to find how much work is going to get to that out. So I still like to do it as there's a couple ways you could set this up. I still am partial, saying this is y equal to 0. This is y equal to, I don't know how high that is. How do we know it's 4? I mean, you're right, Morgan, but how do we know? So what's happening here is that this is 2 feet, so that's 2 feet. So this part here, right here is 3 feet, as is this. And then this is a right triangle. It's a 3, 4, 5 Pythagorean triple. So that's how you know that's 4. So yeah, so that's going to be height of y equals 4. Oops, that's not right. It's y. It's y equals 4. So let's see. I'm going to say once again that this strip is at a height of y, and it's going to have 4 minus y to go. So the work of this slice is going to be, once again, force times distance, which is really volume times density times the distance is going to be 4 minus y. The volume is, I'm just going to say the volume right now is 10 times whatever this length is times dy. So let's call this length L for now. So the volume is going to be the length times the depth, essentially, or width, what do you want to call it? Times dy times our density, which is 62.5, or 4. I'm going with 5. So we need to figure out what L is. We need to figure out what the length of that strip is. And that's where the thing where we actually have to do some work. Sorry, every time I say work, I'm like, we're going to do some work. Oh, that's funny because we're talking about work. I know, it's not that funny, but you take what you can get. So we need to figure out an equation for this in terms of y. And what I want to think about is that the length of this, well, I know that when y equals 0, the length is equal to 2 feet. And that when y equals 4, the length is equal to 8 feet. So there's definitely a linear relationship there, right? Because it's basically just based on this. You could also, if you really wanted to, you could find the equation of that line. If you imagine like the origin being right there, but that just feels like more work than I think we want to do. So here's what I'm going to do. I'm going to say, okay, and the length is going to be some multiple of y plus some constant. And the multiple of y is essentially going to be the slope of this situation. The difference in the L's over the difference in the y's, which is 6 over 4, which is 3 over 2. So that's going to be 3 over 2. And then when y is 0, the length has to be 2. So this has to be 2. And then when y is 4, 3 halves times 4 is 3 times 2, which is 6. 6 plus 2 is 8. So that's what we have. We have that the length is equal to 3 halves y plus 2. There are certainly other good ways of figuring this out. That's the way it works. Remember? Okay, so here's what we've got. We've got that the length here is 3 halves y plus 2. So the total work to pump all this out is going to be the integral of all this, which I would probably write in the following way. I'd probably write it as I bring out the 10 and the 62.5 because they're constant multiples. So write this as 625 integral from as low as y equals 0 to as high as y equals 4 of length, which is this, 3/2 y plus 2, times the depth, which is the 4 minus y, times dy. That's how I would set this up. Just looking at the solutions real quick. I'm curious. Sorry, one sec. I think I wrote these solutions, so they're probably, I definitely wrote these solutions. So they probably are the same. Let's take a look here. Yes, they are definitely set up that way. Although I did use 62.4 in the solutions. Interesting. Right. And really, I just care about the setup. So let's go ahead and do the force. So now, instead of figuring out how much work it takes to pump all this water out, I want to figure out how much force is acting on just one of those trapezoidal plates. I stated it right. The fluid force due to pressure. So here's our trapezoidal plate again. I'm kind of drawing it exaggerated. And I'm still calling this y equal to 0, still calling this y equal to 4. This is 2, this is 8, this is the length of 5, not that really matters. And we know from our previous work that the length of this strip is, I forgot already, it's 3/2 y plus 2. That's the length of that strip. So the fluid force due to pressure on that strip, so the force on just that strip is area times depth times density. Which again makes sense unit-wise, right? Area is going to be in square feet. Depth is going to be in feet, so you're going to have cubic feet. And density is pounds per cubic foot, so the cubic feet cancel out, and you're just left with pounds, which is the measure of force. So it's good to think about if your units are making sense, like if they're going to cancel out the way they should. So let's see, here we get the area of this strip is just the length of that strip, which is 3/2 y plus 2, times dy. So that's going to be 3/2 y plus 2 times dy. The depth is just going to be 4 minus y. And the density is going to be 62.5 or 0.4. I remember it was 62.5 when I was in calculus. When did it change? I don't know. I guess I'm just old. Okay. So then the total force is going to be, well, we're going to add up all the forces when the strip is as low as y equals 0 and as high as y equals 4, right? Because it's a different force the deeper you are, right? Because the depth changes how much water is above it. So that's going to be the integral from 0 to 4 of this monstrosity here. 3/2 y plus 2 times 4 minus y. You put the 62.5 in front, dy. And that's how we would set that up. I can do this if you want me to, but I don't think it's going to show you a whole lot. Right? The only thing you really need to know about how to do this one is that you have to multiply these together. So that's going to be 62.5 times the integral from 0 to 4. 3/2 times y times 4 is going to be 12/2 y or 6y. 3/2 times minus y is going to be minus 3/2 y squared. 2 times 4 is 8. 2 times negative y is negative 2y. And then I guess you could put this and this together before you integrate it. But the integration here should be pretty straightforward. So I'm not gonna do any more with that one. Curious about one thing. It's interesting. Yeah. Why do I feel like I should look at one thing? Oh, that's totally right. Okay. It's just interesting because these integrals are so very similar, right? The only real difference here between these is that this one is multiplying by 10 versus the other one. Right? You essentially got the same stuff. It's kind of neat. Which I guess makes sense because you're talking about the weight of the water. Yeah. You're just not talking about the volume of the water. Okay. Sorry, I was just like, oh, those look really similar. Why is that? Oh, because they're really similar. All right, let's do a spring problem. See if I've got a spring problem. If I have to make one up. The only problem with making up spring problem questions is the numbers sometimes are really super ugly. So let me see. Look real quick here. Pool. Nope, no spring problem there. No, okay, I'll make one up. It's confusing spring problems are okay. It's not that they're confusing, it's just that sometimes the numbers get really nasty when you are having it. So you'll see what I mean. So there's two, in my opinion, there's two varieties of spring problems. There's the variety when you're told how much work it takes, and the variety when you're told how much force it takes. So let's do the force kind first. So let's say it takes, and I'm going to make up numbers and things are going to come out gross. Fine. It takes 40 newtons of force to hold a spring stretched from its natural length of, I don't know, let's say 1.3 meters to a length of 1.5 meters. And then we're going to ask, how much work does it take to stretch from 1.5 meters to 1.9 meters? All right. And the place where people usually make errors on these kinds of problems is by not getting the right limits of integration. So I really, really encourage you to draw a picture, a dumb picture like this of a spring. It's not a good picture, it doesn't have to be a good picture. And label the important values. So we're starting at 1.3 meters. And then we're going to 1.5 meters. And then we're also worried about 1.9 meters. Now here's the thing. Those might be how long things are, but the limits of integration are all relative to the natural length of the spring. So if you're going from 1.3 meters, you're starting at x equals 0 because you've displaced it by 0, right? The distance you have moved the spring from its natural length of 1.3 meters is 0. And here it's going to be 0.2 meters. And here it's going to be 0.6 meters. If you draw this picture, it'll really help. So I really encourage you to do that. Also, the other thing is if you're in the metric system, which I think almost all the spring problems are usually phrased in the metric system, you do want to be measuring things in meters, meaning if they give them to you in centimeters, you need to change them to meters. Okay, so then we know that the force is proportional to the length stretched. So we need to find the stretch, the spring constant. How'd you get 0.2? Because 1.5 minus 1.3 is 0.2. And in a similar way, 1.9 minus 1.3 is 0.6. So it's all about how far it's been stretched from this initial natural length of 1.3 meters. Okay. So in this case, force is equal to the constant, the spring constant times x. And they told us it takes 40 newtons of force to stretch it from 1.3 to 1.5, which is 0.2 meters. Right? It took 40 newtons of force to stretch it 0.2 meters. Or I should say to hold it stretched at 0.2 meters, because the language there is slightly important. So let's see. So K is going to equal 40 divided by 0.2, which is going to be 200. Great. So now we want to answer this other question. How much work does it take to stretch it from a length of 1.5 meters to a length of 1.9 meters? Well, that means you're starting at a displacement of 0.2 meters. And you're ending at a displacement of 0.6 meters. And you're integrating force times distance. Okay, so now we're just going to integrate. We're going to get 200x squared over 2, so 100x squared. I happen to make up nice numbers. I got lucky here. From 0.2 to 0.6. And then we're going to plug that in. And we're going to get 100 times 0.6 squared, which is 0.36, minus 0.2 squared, which is 0.04. And 0.36 minus 0.04 is 0.32. So I get 100 times 0.32, which is 32 joules. Okay, let's do another one that's going to be similar but have an important difference. Let me erase the back side here while give you a chance to look at that. Oh, I'll be careful here. Need more room. Okay, so any questions about this one before I go on to the similar, a little bit different problem? Okay. Sorry, I'm feeling foolish this afternoon. All right, so hopefully everybody had a nice break yesterday from not going to class and got to maybe relax a little bit. I know just because you don't have school doesn't mean you don't have school work to do, but hopefully there was some sort of taking a break for a moment everybody got to have. And then in a couple of weeks, we'll have Thanksgiving break, which will still be a break, right? Even if we don't have all that much to do. Anyway, I'm just making stuff up. So pay attention to the difference in phrasing. In this problem I wrote, it takes 40 newtons of force to hold a spring stretched from its natural length of 1.3 meters to a length of 1.5 meters. And now I'm going to say it takes, I'm just saying numbers are probably not going to be nice here, 8 joules of work to stretch a spring from its natural length of, I don't know, let's call it 110 centimeters to a length of 100 and, no, let's not be, don't be stupid, James, to 150 centimeters. How much work would be required to stretch it from a length of 130 centimeters to 170 centimeters? Which I think is kind of an interesting question, because they're telling us it takes 8 joules of work to stretch it 40 centimeters, and then we're asking how much work does it take to stretch it a different 40 centimeters? And our intuition here should be that it's going to take more work, because again, the further stretched out the spring is, the more work it's going to take. So these, right, from its natural length to 40 centimeters out is kind of the easiest 40 centimeters you could possibly stretch it. If you've already stretched it out 20 centimeters and you're trying to stretch it another 40, it's going to be harder to do, so it's going to take more work. Here's the difference in how we solve this problem. No one said anything about how much force was required to hold it at a certain length. They said it took so much work to stretch it to that length. So instead of starting back, whoa, Jade, before I get even close to getting there, I should draw a picture of the spring. Here's my dumb looking spring. And I know I care about 4 different lengths, 110, 150, 130, 170. So I'm just going to draw those in. So 1, 2, 3. And again, 110 centimeters is my natural length. There's 130 centimeters, 150 centimeters, 170 centimeters. Might have made the numbers too easy. Oh well. So then natural length, that's x equals 0 meters. 130 centimeters is how many meters away? Well, it's 20 centimeters away from 110, so it's 0.2 meters. And in fact, all of these distances are 0.2 meters away from each other. So this next one's going to be 0.4 meters from the beginning. This next one's going to be 0.6 meters from the beginning. Right? We always are measuring in relation to the natural length. Okay. So they told us that the work it took to stretch it from here to here was 8 joules. So the work, which is the integral from 0 to 0.4 of k times x dx, is equal to 8. That's the difference here, is that in the other problem, when they tell you force, you can just solve for k by dividing both sides by whatever the amount of displacement is. And k equals force divided by x. Here, we can't just divide. We have to say, oh, well, work you get by integrating this thing. So if I know how much work it takes, I have to do this integral to solve for k. All right. So let's see. We're going to get kx squared over 2 from 0 to 0.4 is equal to 8. I'm plugging the 0.4. You get k times 0.4 squared over 2 is equal to 8. And then plug in the 0, you get 0. Multiply by 2. And 0.4 squared is 0.16. And then 8 times 2 is 16. And then divide both sides by 0.16. And k is equal to 16 divided by 0.16, which is 100. All right. And then we're going to do the rest. So the rest is, all right, I want to figure out how much work we have to do to get from here to here. So we're going to integrate from here to here, 0.2 to 0.6. So the work it's going to take to get from 130 centimeters to 170 centimeters is going to be the integral from 0.2 to 0.6 of k times x dx. So integrating this, you're going to get 50x squared over, not 50x squared over 2, just 50x squared. Or you're going to get 100x squared over 2, which is 50x squared, from 0.2 to 0.6. So you're going to get 50 times 0.6 squared minus 50 times 0.2 squared. And then we're going to end up with 50 times 0.36 minus 0.04. These numbers happen to be similar just because that's what my brain thought of this time. So I get 50 times 0.32, which I'm not good at, but I know that 50 is 100 divided by 2. So I can say that this is 100 times 0.32 divided by 2, and then 100 times 0.32 is 32, and then 32 divided by 2 is 16. So look, that's kind of interesting. It actually takes twice as much work to go from 0.2 meters to 0.6 meters than it did to go from 0 to 0.4. That's kind of interesting. I mean, it's mildly interesting. All right. Okay. Let's see, what else have I got here? Lots of things. Let's go back and look at this. You. Okay. I guess we should do a moment problem. Yeah. Okay, let's do a moment problem. So for those of you that aren't doing moments yet, or not at all, possibly 21B, I will say, even if you are doing them in 21B, you might end up doing them later on in 21C or 21D, but you also probably are all taking the Physics 9 series at some point, and you definitely talk about moments in the 9 series. So even if you think you're escaping them in 21B, you're definitely not escaping them in the Physics 9 series. And I imagine that anyone taking the 21 series is probably taking the Physics 9 series, so you should definitely want to know about movements. They're also kind of interesting. So let's look at this problem, which is problem 3 from the practice exam 2A. So it says, consider the region R in the first quadrant bounded by the graphs y equal to x cubed. Well, this kind of trash. And x equal to 1. We got this kind of shape. It looks like, this. And x equal to 1 looks like this. We're in the first quadrant, so we're looking at this. So there's our region. And we are being asked to find mx, the moment of the region about the x-axis. So find mx, the moment about the x-axis. And assuming constant density. Delta. All right, so if it's up to me, I'm going to try and make my life as easy as possible. Meaning, I really, really, really would prefer to think about it as the lever arm length being easy. What I'm trying to say, and kind of taking forever to say it, is that I would really like to do a moment around the x-axis using a horizontal strip. And thinking about that horizontal strip all being the same distance y away from my axis. So the moment for this strip, again, so the moment of a thing is the lever arm length times the mass of that thing. The mass of that rectangle is the area of the rectangle times the density. So it's the area times the density. The density is just the density in this case. The area is the area of a rectangle, which is the length of it, right function minus left function, times the thickness, which is dy. So the right function is x equals 1. The left function is x equal to the cube root of y. If I solve this for x, you get x equal to y to the 1/3. So the area of this strip is 1 minus y to the 1/3 times dy. So that's the moment for this strip around the x-axis. And so then, then the total moment around the x-axis is the integral from how low this strip goes to how high this strip goes. And this point of intersection is the point 1, 1. If x is 1, y is x cubed. Y has to be 1 as well. So we get the integral from 0 to 1 of y times 1 minus y to the 1/3 dy times delta. And then the integral is not terrible, right? It's going to be delta times the integral from 0 to 1 of y minus y to the 4/3 dy. We anti-differentiate. We get y squared over 2 minus y to the 7/3 times, the 7/3 times 3/7 from 0 to 1. So we get delta times, so I plug in 1, I get 1/2 minus 3/7. I plug in 0, I get 0. You want to re-emphasize, I know I said this a lot earlier on, so I want to remind you all, you don't always get 0 every time you plug in 0. It's just that when you have your variable to a power, you do. So just remember, you should still think, if I plug in 0, do I really get zeros? Oh yeah, I do get zeros. Okay, great. So then that's going to be 7/14 minus 6/14, which is 1/14. going to be delta over 14. So that is the moment around the x-axis. And I really want to remind everybody that when you're going around the x-axis, the lever arm is y. Y is how far you are from the x-axis, just like with surface area. Okay. Second part of this problem. Oh. I could. Okay, fine. Yes, that's a fair question, Morgan. I could definitely try using a vertical slice. So using a vertical slice, here's my vertical slice. And the problem with a vertical slice around the x-axis, not that it's insurmountable, but the thing that makes it less nice is that that vertical slice isn't all the same lever arm distance from the axis. So what we do is we pretend it is. We pretend all of this mass is centered at the center of the rectangle. So the question is, what's my lever arm now? Well, how far is the center of that rectangle from the axis? Well, it's half the length of the rectangle. In most cases, I say we average the two functions, but in this case, since one of them is 0, it's just really half of whatever that top function is. So here the lever arm length is 1/2 x cubed. It's really 1/2 x cubed plus 0. In general, if you're doing it the way that's less nice, where you're like, oh yeah, when your strip is perpendicular to the axis that you are momenting around, then your lever arm is always the average of the two functions. So then we do the same thing. The moment of our strip is going to be lever arm times mass, which is just area times density. And that's it. Lever arm times area times density. So that's going to be 1/2 x cubed. The area of that strip is the area of that rectangle, which is the height, which is also x cubed, times the base, which is dx. So when one of your functions is 0, the formula ends up being that the total moment around the x-axis is going to be 1/2 the integral of your function squared, which is exactly what we have here. Right? It's 1/2 of x cubed times x cubed, or 1/2 of x cubed squared. When you've got two, right, when your function, when you're not just right against your axis that you're momenting around, it ends up being the more complicated version, which is 1/2 top function squared minus bottom function squared. No, yeah, the lever arm is always so when you're doing it this way, the lever arm is the average of the two functions. When you're doing it this way, the lever arm is just how far it is from the axis, which is y. So yeah, here the lever arm is 1/2 the function y equals x cubed plus the function y equals 0. It's just that if it was something else, like if your picture was more like this, right? So like if this was f and this was g, then your lever arm length would be the average of f and g, because you want to be in the middle of f and g, which is the average of f and g. So in this case, you're going to get 1/2 the integral from 0 to 1 of x cubed squared dx. Just don't forget the delta. So that's delta times 1/2. That looks terrible. My writing gets so sloppy in here. Integral from 0 to 1 of x to the 6 dx. And oh, look, it works out. We get delta over 2. Integral of that is x to the 7th over 7. From 0 to 1, we plug in 1, we get delta over 2 times 1/7, which is delta over 14. Same as before. Delta over 14. But here's what I would say. If you have the choice, it is usually going to be easier to draw your strip parallel to the axis that you are momenting around. I don't know if there's a better way to say it. Parallel to the axis that you're finding the moment about. But let's just say momenting. It sounds more interesting. So I say so a lot. So yeah, so if I'm given the choice, if I'm going around the x-axis, I'm going to try and draw a horizontal strip. Now, sometimes it's not going to work out great, and I'm going to be stuck just having to draw a vertical strip. Like when we were doing areas of things or volumes of things, and like we could draw a horizontal or a vertical strip, but drawing one of those strips made it so like you had to break things up into multiple pieces. You wouldn't want to do that. So usually we try to always default to doing one interval versus multiple intervals. Well, let's look at the rest of this question. The rest of this question is to find, the rest of this question is actually fairly easy. So the rest of the question is to find the coordinate y bar. So we know that mx at the moment around the x-axis was delta over 14. Now we're being asked to find y bar, which is the y coordinate of the center of mass, which is the moment around the x-axis over the total mass. We already found that. We have to find that. That's easy though. The total mass, if your density is constant, the total mass is just the area times the density. So we just have to find the area of this region. So that's going to be the integral from, you could do whatever you want. You could do things in terms of y, or you can do things in terms of x. I'm going to do it in terms of x because that just feels normal. Integral from 0 to 1 of x cubed dx times your density. Integrate that, you get density times x to the 4th over 4. 0 to 1, that's going to be density times 1/4. So then y bar, your y coordinate of the center of mass, is going to be delta over 14 times delta over 4. Flip and multiply, deltas cancel, you get 1 over 14 times 4 over 1, which is 2 over 7. Okay. So the y coordinate is 2 over 7, well below the halfway mark, which makes sense though, because a lot more of the mass of this plate is below the halfway height, or I should say below y equals 1/2. Right, there's 1/2, and like 2/7 is a little bit more than half of that. So like that right there, so somewhere on this horizontal line is the center of mass. We could also find the center of mass for the x coordinate, or I should say, we could find the x coordinate of the center of mass to find the moment around the y axis. Then we would want to use the vertical strip, right? It definitely makes sense to use the vertical strip here because then your lever arm is just x. If I'm trying to find the moment around the y-axis, it's just going to be the integral from 0 to 1, right? 0 to 1 of your lever arm times your area of your strip, which is going to be x cubed times dx, and then we want the mass really, so we want the delta up there. And so then this becomes pretty easy. It's going to be delta. Integral of x to the 4th is x to the 5th over 5 from 0 to 1. That's just going to end up being delta over 5. And so we end up getting that my is delta over 5, and x bar is delta over 5 over delta over 14. Oh, sorry, delta over 4, not delta over 14. And that ends up being 4/5. So the center of mass, x bar, y bar, would be the coordinates 4/5, comma 2/7. Which again, if you look at this shape, makes sense, right? Definitely, of the, like if you think about the four corners of this shape, not that this is really a corner, but certainly most of it is in the lower right corner. So it makes sense that the center of mass is way far to the right, right? From 0 to 1, it's at 4/5, and it's definitely lower, right? From 0 to 1, it's 2/7, which is like the lower quarter. Yeah, right. What else? Should we do another arc length problem? It's been a while since we did an arc length problem. see. There was something. Sorry, one sec. So I want to find the length of y equals x to the 3 halves on the interval from 0 to 4. Create an arc length problem around an axis parallel to the strip and not the x or y axis. Okay, but parallel to I guess I'm not sure what you mean by parallel here, Morgan. Like you want me to use the problem. So when I'm thinking arc length or surface area, I'm not so much thinking a strip as like a rubber band. Let's do this arc length problem first, and then actually the second part of this is to do a surface area problem. So we can talk about that, and we'll talk about either way. So to find the arc length of this, we're going to do the arc length, and then really this is remembering a formula. This is going to be the integral from 0 to 4 of ds, which is the integral from 0 to 4 of the square root of 1 plus the derivative of this squared. So it's the derivative of x to the 3 halves squared dx. So this case is going to be the integral from 0 to 4 of the square root of, let's see, 1 plus the derivative of x to the 3 halves is 3 halves x to the 1 half squared dx. And then when we square that, we get squaring that, you get 9/4 x dx. You can do a u sub here or not. I'm going to think of this as 1 plus 9/4 x to the 1 half. If it was just x to the 1 half, I know that my integral would be x to the 3 halves times 2/3. So I'm pretty sure this is going to be something like 1 plus 9/4 to the 3 halves times 2/3. That's almost right. Let's take a look at how it's not right. If the integral of this were that, which it's not yet, then the derivative of this, oh, sorry, it was really not, there's not an x there. Sorry about that. But if the integral of this was that, then the derivative of this should be that. But here's what happens when I take the derivative. The derivative of 2/3 times this to the 3 halves, well, let's see. The 3 halves comes down. 2/3 times 3 halves is 1. So I get this 1 times this to the 1 half power, but then I have to use the chain rule and multiply by what? And you're very close. So yes, I need a 4/9 because I need a 4/9 to counteract the 9/4 that I would multiply by if I was going to take the derivative. So yeah, so I have to divide by the coefficient of x, I have to divide by 9/4, which is multiply by 4/9. So that's what we get from 0 to 4. And let's see, we plug in, so 4/9 times 2/3 is 8/27. If I plug in 4, I get a number that isn't as nice as I wanted it to be. Oh, well, that's life. Sometimes the numbers aren't nice. I plug in 4, I get 1 plus 9, which is 10 to the 3 halves. Minus, if I plug in 0, I get 1 plus 0, which is 1 to the 3 halves, which is 1. And I would leave my answer like that. Excuse me. Yeah, it's too bad. Should have been a bit better for this. Anyway, it doesn't matter. So let's talk about surface area. So let's say I want to find the surface area of this monstrosity. Oof. Yeah, we can. Okay. Yeah. So we'll talk about setting up the surface area around either axis and then talk about how one of them we can solve. So I want to find the surface area of y equal to x to the 3/2 revolved around either axis. With the x-axis over here, with the y-axis over here. So here's what I would remind everybody of. You're thinking surface area, you're thinking, okay, you're thinking surface area is the integral of 2 pi r ds, where r is the radius of your thing. So let's draw a picture here. So I draw this picture, right? And I can draw my curve, okay? I'm going from what, 4 to 9? Sorry, 0 to 4. 0 to 4. Yeah, 0 to 4. Okay. Sorry. So my graph looks something like this. I don't really care what it looks like so much. And I'm going around the x-axis. So I've got some shape, looks kind of like this. And I'm thinking about this rubber band here. And I want to know what's the surface area of that rubber band. Well, again, it's 2 pi r ds, where the radius is how high or how far we are from the axis of rotation. In this case, is the radius x or is the radius y? Excellent. Yeah, it's definitely y, right? Because if you're going to the x-axis, you are y away from the x-axis. And that's something that's pretty much, as I think you guys have gotten used to seeing now, that's always true. Right? If you're talking about how far it is to the x-axis, you're saying, oh, I'm thinking of a y thing. And vice versa. If you're going to the y-axis, it's an x thing. So in this case, that's going to be 2 pi y ds. But the problem is, I mean, I guess it's not a huge problem. We could probably try and do this in terms of y if we really wanted to. But I've already got things in terms of x. So I would much rather write this as 2 pi times what y is equal to times ds. So the integral for this one around the x-axis would be the following. The total surface area would be the 2 pi times the integral from 0 to 4 of x to the 3/2 times your ds. Now, ds didn't change. This is still ds. Or even better, that right there. So I'm just going to, right, some people will often ask you to do an arc length and a surface area problem for the same function. ds isn't going to change in that situation. You should use the work you've already done, right? Don't calculate this again. Just use the fact that ds is 1 plus 9/4 x to the 1/2. Or the square root of 1 plus 9/4 x dx. Now, unfortunately, I don't think we can actually do this problem because, I don't think, it might not even be doable. So that's how you set this one up. On the other hand, if I was going around the y-axis, then my radius would be x. And so the surface area, which I'm not going to draw, the surface area of my band here would be 2 pi x times ds. And then I can say that my total surface area is the integral from 0 to 4 of 2 pi times x times my ds, which is still the square root of 1 plus 9/4 x dx. And this one we actually can calculate, but we do have to do a u sub with a back substitution. So here's how this one works. You set u equal to be 1 plus 9/4 x. Wow. I can write things. And then your du, your derivative, well, derivative 9/4 x is just 9/4. So du dx is 9/4, or du equals 9/4 dx. Solve for dx. So 4/9 du equals dx. And then start rewriting your integral. So my integral is going to become 2 pi. Integral, I'll worry about the 0 to 4 in a second. Dx is 4/9 du. I'm going to go 4/9 out in the front. A du over here. Square root of 1 plus 9/4 x is just the square root of u, or u to the 1/2. And then x to solve for. So multiply, or sorry, I guess subtract 1. And then multiply times by 4/9. So u minus 1 times 4/9 is equal to x. And that's what's going to go here. 4/9 u minus 1. Sorry, that's getting kind of scrunched up. So it's a 4/9 times u minus 1. That's x. And then there's your square root of u. And then there's your dx. So there is a 4/9 in front, right? So there's two 4/9. There's the 4/9 you get from this right here, right? Dx is equal to du times 4/9. And then you also have the back substitution part, which also happens to have a 4/9 in it, where you solve this for x. X is u minus 1 times 4/9. And then I'm going to erase over here to integrate this thing. Oh, I didn't change the limits of integration. So I'll do that over here. So let's see what I've got. I've got 4/9 times 4/9 times 2 pi. So let's see, that's 16 over 81 times 2. That's 32 pi over 81. That's my 4/9 times 2 pi times another 4/9. And then I've got the integral of u minus 1 times u to the 1/2. And my new limits of integration, well, if x is 0, u is going to be 1 plus 9/4 times 0, which is 1. And if x is 4, u is going to be 1 plus 9/4 times 4, which is 1 plus 9, which is 10. Finally, we distribute the u to the 1/2. So you get 32 pi over 81. Integral of u to the first times u to the 1/2 is u to the 3/2 minus 1 times u to the 1/2. Whew. Okay. And then finally, 32 pi over 81. When we integrate this, we get 2/5 u to the 5/2 minus 2/3 u to the 3/2 from 1 to 10. That's pretty ugly. And then you would plug in the 10 and not do anything with it, and plug in the 1 and get some terrible answer. So Morgan, did that address your question of what you were asking about, like an arc length or a surface area parallel to the strip? Was that what you kind of meant? Okay, what can I do in the last 9 minutes? Let's see. Let me ask you guys a question. Have you had to do any problems where the density wasn't constant? Okay. All right, cool. Then we'll take that as a no. Let's see. Let's do one more. Okay, yeah, I know what to do. We'll do another. I don't want to do a leaky bucket problem, because leaky bucket problems, there's so much thinking. but let's do a bucket problem, and if we decide to, we can make it leaky at the end. So let's say I have a bucket. It weighs 10 pounds, because it's gigantic. It's full of water. It's got 50 pounds worth of water. Speaking of which, it's funny. So my friend Sarah, who's also one of the specialists, visited Africa this last, what was it, January. Visited a friend of a friend who's in the Peace Corps there, along with her husband and their son. And she was telling me that, oh yes, I actually did have to lift water using a bucket out of a well, and it was a little bit leaky. So it really felt like, oh my gosh, the leaky bucket example was really like a real thing. But her bucket did not lose all the water when it got to the top, so it felt more realistic. Anyway, here's an example. So we got a bucket, it weighs 10 pounds, it's full of water, 10, and it's got a rope. The rope is 30 feet long. Okay, now I want to know how much work. Oh, and the rope weighs 10 pounds. Okay. So, how much work to lift the whole thing, not quite all the way to the top of the well, to 5 feet below the top. Okay, let's draw ourselves a picture. So we've got the top here, got our rope, got our bucket, at the bottom. All right, and I do think for these leaky bucket, or any kind of bucket problem, it does seem to be easier to me to call the top y equals 0 and the bottom y equals however long your rope is, in this case 30. Okay. And we're trying to get it all the way up to here, which is y equals 5. Now, the part whose weight isn't changing or whose rope isn't the rope, that's the easy part, right? So in this case, since we're not losing any water, the work for the water and the bucket is going to be super, super easy. So the work for the water and the bucket is just going to be their combined force, aka their combined weights. The water is 50 pounds, the bucket is 10 pounds, so that's going to be 60 pounds of force times how far it goes, which is going to be 25 feet. And that's going to be 150 foot-pounds. Sorry, 1,500 foot-pounds. 150? 1,500. So the part that's not really changing, that part's always just going to be like, oh yeah, it's just however much it weighs times however far it goes. You could also set this up as an integral. You could also set this up as the integral from 5 to 30 of 60 plus 25 dy. That would also work just fine. The hard part's going to be the rope. The rope, which is 30 feet long, weighs 10 pounds. So the rope, 30 feet long, weighs 10 pounds. The density of the rope is 10 pounds per 30 feet, or 1/3 of a pound per foot. And for these ones where you're not lifting it the whole way, to me, I just find it easier to think of it in the way that I don't usually find it, which is that I'm going to take all of the rope and think about it moving a small distance. So let's say we've lifted the bucket up to here. So we've lifted the bucket up to here. And it still has, ooh, I have to be careful. So yeah, this is why I do it the way I want to do it. So we've lifted the bucket here, and we're going to ask, okay, how much work does it take to move it that small distance? I should say, we're not really talking about the rope. We've lifted the rope bucket here, and we're asking how much work it takes to move the rope this small distance. Okay, so how much work to move the rope that small distance? Well, it's force times distance. I'm not just moving this small section, I'm moving all of this rope this small distance. How much rope is there? What am I calling this part here? Just calling it y, right? If you're ever, when you're measuring from y equals 0, you're usually calling it y. That's why it's easier to set this one up like this. And then this would be 30 minus y if you cared. So the weight of this rope is the length of the rope, y, times the density of the rope, which is 1/3, times the distance it's traveling, which is dy. So then we have to integrate. This is where I was kind of caught up. The total work for the rope is going to be, well, if we think about this starting at the bottom, we're going to be, I'm going to be making a mistake, but I don't think about stuff for a second. So we have to think about the fact that we're just moving these small distances, right? So we're moving small distances from, we want to end at y equals 5 and start at y equals 30. Or really, we want to integrate from 5 to 30. And I feel like that part can also be a little bit confusing, right? But that's the region where we want to see the rope move between, right? We don't care about the rope up here so much. And we care about that rope, but we're not going to be moving those last 5 feet. So it's going to be this, which would end up being 1/6 y squared from 5 to 30. It ends up being 1/6 of 30 squared minus 5 squared, which is some number, 875. So then you would add them together to get the final answer.